Hi everyone, I'm Shayan, and today with Finn we are going to present our work compiling distributed system models into implementations with Pico. So first, I'm going to describe the problem. Today, distributed systems are an essential part of the modern software stack. We can see them everywhere, as in the cloud services and in the infrastructure tools. However, despite being widely used, distributed systems are hard to build correctly because they have to deal with the asynchronous network, failures, concurrency, and these together make distributed systems so complex. Even we can see the system deployed in production often have bugs. In this slide, we can see several real-world examples of bugs in the distributed system that have caused outages in the systems. And we can see that even this happens to the largest cloud providers such as AWS, Google Cloud, and Microsoft Azure. So we know that distributed systems are built based on the distributed protocols, but it's actually kind of hard to correspond the final implementation of a system with its high-level protocol design, because protocols typically have edge cases and production implementations resort to ad hoc methods for handling these cases. And these ad hoc methods are not necessarily correct. So we would have some behavior in the implementation which is not in the protocol itself. So we can see that the key problem here is the gap between design of the protocol and final implementation of the system. But there are several previous works that try to address this problem. The first line of work tried to use proof assistant to prove some properties about the system, for example, some safety or liveness properties for the system. These methods can achieve a high verification degree, but they require lots of human effort. For example, in the Iron Fleet paper, they said that it took more than 3 person-years for them to build 2 distributed key value stores using Paxos and primary backup replication. Some other work tried to model check the system's implementations. Model checking here means exploring all possible executions of a system to see if it satisfies the required properties or not. Here, because the implementations are so complex, we would encounter the state space explosion problem very quickly with only exploring a small number of relevant states. And the final group of work tried to use systematic testing, tracing, and debugging. Although these methods can reveal some bugs in the final implementation of a system, but they are incomplete in a sense that they cannot actually verify correctness of a system. So they can just find specific kinds of bugs. So here is our work Pico, and the main idea is compiling distributed system models into implementations. Models here are abstract specifications of systems. This abstraction of models allows us to explore a large number of states during model checking. And finally, we generate an implementation automatically from the verified model. So let's see Pico in more detail. Pico is actually a compiler from models in Modular PlusCal language, which I call it MPCal for short, into implementations in the Go programming language. As you can see on the figure on the right, user writes a model in the MPCal language, and then Pico compiles it into a Go program. Then you can run the Go program in the distributed setting. So this is the very high-level workflow of Pico. But the point is that it's also possible to verify the MPCal models. So by using Pico, user can define the desired properties for a model and use a model checker to see if the model satisfies the properties or not. Here we focus on the mult checking for verification, but it's also possible to use theorem provers such as T-labs for the verification. So if we put these two diagrams together, we would have this diagram for the whole Pico diagram, for the whole Pico system. So we can see that this diagram actually has two paths. The left path that focuses on the verification and actually verifying an MPCal model, and the right path that goes to implementation and getting a concrete implementation from an abstract MPCal model. So next we talk about the MPCal language and verification. So here we see the same diagram as before, and we're going to focus on the left part. So if we look at this picture and zoom into this, we would see the figure on the right. So in more detail, what happens is actually for the verification is that first the user writes system model in MPCal, and then Pico compiles it into PlusCal. And PlusCal is a modeling language. PlusCal code also can be translated into TLA Plus, which is another modeling language. In TLA Plus, user defines the correctness properties, and finally the TLC model checker validates or produces a counterexample. Next, for the background, we're going to quickly take a look at the TLA Plus and PlusCal languages. TLA Plus is a declarative language for modeling systems. Each TLA Plus model consists of several predicates that defines the system's initial state and transition relations. As an example of transition relation, here we have a simple bank transfer that says if Alice has enough savings, then transfer an amount of money from Alice's account to Bob's account. Also in TLA Plus, we can define the required properties. For example, here the property that we want is that the balances must be always non-negative. And finally, the model checker validates this property or produces a counterexample. So we can see that the TLA Plus language is actually kind of a math language, and it's so different from a typical programming language. So to make it easier for programmers, Lamport came up with another language called PlusCal. PlusCal is a procedural language that can be compiled into TLA Plus. PlusCal is pretty similar to pseudocode and has familiar constructs such as if and while statements. Here we see the same bank transfer model, but here in PlusCal. A PlusCal model has some processes, and these processes are kind of similar to operating system processes, but they're sequential. Although different processes can run concurrently in PlusCal. Each process in PlusCal has some labels, and each label corresponds to a TLA Plus transition relation. So this transfer label here is the same as the transfer transition relation that we had in the TLA Plus slide. Now we have seen the background, so let's see our new language, MPCal. Today, people write TLA Plus and PlusCal models and then manually translate them into implementations. This process is both tedious and error-prone. So our goal with Pico is making this process automatic. And we are going to do that by building a new language on top of PlusCal, which we call it MPCal. But first, let's see what's the problem with PlusCal and why we cannot automatically compile it into an implementation. Here we have a blocking network read code both in PlusCal and Go. But first, let's take a look at the PlusCal code. Because there is no networking semantics in PlusCal, we should somehow simulate it. So here we modeled network as a queue, and after waiting for the queue to be non-empty, we did some list manipulations to read the first message in the network. So we can see that almost all the PlusCal code here is for the model checker because we have to simulate the network behavior for the model checker. But if we take a look at the Go implementation, we can see that it's completely different because in Go we have actually the networking semantics and we don't have to simulate it. So this Go implementation is pretty straightforward and just reads the first message from the network. So a solution might be using PlusCal macros. PlusCal macros are similar to C macros, and the macro call will be replaced by its body. So by using macros, network reads becomes a one-liner on the PlusCal side, and the macro body can be replaced with a concrete implementation on the Go side. But the problem is that it's not actually clear how to provide an implementation for this read network function. Because except its name, it's not clear that how it actually related to the network, because from its two other input and outputs, we cannot understand how it should do the networking semantics. Also, another problem that we have is that each process views the network as a global state and can do anything with it, which is not true in the reality. In reality, processes have the local view over the network. So our solution is the MPCal language, and the main idea of MPCal language is separating the system definition from its environment. So for doing that, MPCal introduces two new kinds of macros. The first one is called an archetype. Archetypes are processes that only contain the system definition. Archetypes has parameters, and these parameters are environment instances that the archetype can access. So in this case, the server archetype has access to the network. And here, all the networking semantics becomes reading and writing to the network environment instance. And we should define all the model checking and environment behavior somewhere else, because as we said, archetypes only contains the system definition. Also, if we take a look at the Go code, we can see that it's now actually can be possible to have an automatic Go compilation, because now in addition to self and MSG variables, we also have access to the network variable, which allows us to actually implement the networking semantics. We said that model checker and environment behavior should be defined elsewhere. So here is their place. Mapping macros contain the model checker and environment behavior. So when we have a network read in an archetype, it will be expanded to the read part of the mapping macro. And in the read part, we have defined the blocking network read semantics that we had before, but now they're all in the archetype. We also have the same thing for the write. So a write statement to a network instance will be expanded to the write part of the mapping macro. So as we said, mapping macros only contain the model checking code, so they won't be compiled into Go. So if we put this all together, the elements of MPCal language, first we introduced archetypes that only contain the system definition. Then we saw mapping macros that define the environment behavior, and finally we have instances that configures archetypes and mapping macros with each other. So let's see a kind of real world example. Our example is a web server that receives a message from a network and then reads a web page from a file system and returns the result back to the network. Here is the server modeled in PlusCal. It has two main parts. First, it reads the message, and then in the second part, it sends the page back to the client. As we said before, almost all the read message part is the model checking code. And in the send page part, because we want to have a buffered network, we had to simulate the behavior of a buffered network here. Also, another problem is that file system interaction is not explicitly modeled, and just a constant has been considered as the file system output. But in MPCal, we would have this code. So we have an archetype server that has access to network and file system environment instances. And in the read message part, the network semantics becomes easy, and it's just a one-liner reading from the network instance. And in the send page part, the file system interaction becomes explicit. So now we're explicitly reading from the file system. Here is the TCP channel mapping macro that defines the networking behavior. In the read section, we define the blocking network read semantics, and here $sign variable is the variable being mapped, and the yield statement returns the result of the read operation. In the write section, we define buffered network write semantics, and here $sign value is the value being assigned to the mapped variable. And here is our very simple file system that is both read-only and always returns a constant response for the reading. So putting this all together, here we defined an archetype server that is configured with the related mapping macros, and the archetype defines the system definition, and mapping macros define its execution environment. Still, same as PlusCal, we defined network as the global state, but the point is that here with this function mapping syntax, archetypes has only a local view over the network, so they don't have this global access to the network. So if you want to compare PlusCal and MPCal with each other, in PlusCal, the process of translating a model into an implementation is manual and error-prone. This also makes protocol updates difficult because they have to be applied manually, and keeping the model and implementation in sync is not easy. On the other hand, MPCal allows automatic implementation generation by making the system definition and its environment separated. Next, Finn talks about the implementation generation in Pico. Thank you.
So, yes, as Shayan said, we'll be talking about how Pico can generate an implementation for your MPCal model. So let's get back to our big diagram with all the aspects of Pico, and we'll now be focusing on the other path, where we go from Modular PlusCal through into concrete land, where you actually create something that can run. So if we zoom in, you'll notice that the implementation part isn't exactly just straightforward, a bunch of Go code. There is some compiled Go code. There are also quite a lot of runtime libraries, and there are things the user has to provide involving setup and some degree of configuration. To talk through the general workflow here, you start with Pico generating some Go code. That Go code then needs to be linked together with its environment in a somewhat customizable way. And then you can deploy that using standard deployment techniques for Go code, and everything should be as expected at that point. So we need to go into how points 1 and 2 actually work. First, let's talk about linking abstractions with concrete implementations. Pico doesn't, as a design point, MPCal does not really expose how a resource will be implemented. It provides a model of it, certainly, but that model does not need to have very much to do with how a practical implementation would actually perform whatever tasks are necessary to implement that resource. And in any case, we wouldn't want to assume too much about those implementations because you might need some pretty diverse things as an implementer. So what we want to do is we want to support diverse implementations. There are some very strange things that MPCal will do as it executes that we need to support in terms of non-deterministic program flow. And we also want to have as bug-averse as possible a compilation process. So we don't want to do anything too complicated in the compiler if we don't have to. And then to speak more holistically about our objective, every execution of the resulting system has to map to something the model might have done, so it has to be a refinement. Our environment is abstract in MPCal, and in Go it needs an implementation that does something the abstract environment could plausibly have been seen doing. And to get all of this right, we need to understand how TLC explores behaviors defined by a model. But first, let's talk about why there isn't much to say about our compilation process. We have essentially a one-to-one compilation from MPCal to Go code, and all the complication happens in our library code. We did this to keep everything as simple as possible, so that you could debug and figure out the Go implementation of all the processes we need to have, separate from a compiler, which is an equally complex piece of software, and it pays to have those two things somewhat separated. So let's talk through this very simple example. So up top we have this a simple statement in MPCal, and it would get compiled roughly like so. So first you want to evaluate that self reference to read it, and we just call out to part of the runtime code. Then you want to apply the indexing here, which you do also by calling out to some library code and doing some Go error handling. And lastly, no exceptions here. Even if you might remember that message is actually a local variable in the original example we pulled this line from, it doesn't matter. Pico doesn't actually pay attention to much context here, and that really does also get compiled to a library call as well, with the error handling as you might expect it. So, now that we've explained why it's not very important to look at all of our code generation, because it's relatively simple and does more or less what the MPCal does, let's dig into an expansion of our running server example from the MPCal section and try to understand everything else. So essentially we've pulled out the server, we've added a client. Point of interest, you might not normally expect to think about this, but in MPCal you have to be explicit about any user interface that you might have. So in this case, the client needs to be controlled in terms of what requests it has to make and what outputs those requests give. Someone has to witness those things, so we have to provide that as input-output as opposed to just assuming it, like you might do in an implementation, which will just do that by side effects. So to quickly flash you the code, the right-hand side is exactly the same as we've shown before. We've got a server that will serve as requests in a loop, and we have a client which will send requests in a loop by reading a request from paths, passing it into the network, and then expecting a response from the network that's a response to that request, which presumably comes from the server. So to expand a little bit on that previous diagram, what we have to really emphasize here is this abstraction boundary. So the generated code that does more or less what the MPCal said is in that little box. A client and a server archetypes don't really know how file systems, networks, or even the little input-output channels work at all. We have to get all of that right by providing things that plug into the generated code. So now let's talk about why that can be a bit hard. So labels define atomic steps is really one of the big takeaways you have to remember when trying to understand how to implement MPCal. So that means all of a step happens or none of it, and there is no in-between. If an in-between happens, the model does not represent that, and we have no way of understanding what that means relative to anything we proved about that model. So what's tricky is most programming languages don't work like that, and a lot of I/O processes don't really work like that either. It's not really how you think about most sort of practical code. So that causes us some difficulty in terms of needing to work around that. And also, more complex models will have this little construct called an either, which allows you to branch non-deterministically between multiple choices. Implementations do actually do this in practice, but they don't really say it like that. And again, this is an extremely general theoretical construct which needs to be somehow converted to talk about the practicalities you need when you're, say, I don't know, reading between one network socket and another network socket. That's obviously a thing most servers will do, but to translate the generality of how it's written in MPCal to a practical implementation will take some doing, and that's why all of this summarizes the actual challenges of implementing MPCal. So back to our running example. Let's imagine that we have a server running and 2 clients, and let's try and understand TLC's point of view for how it understands what is and isn't possible. To start with, everything's in labels, as we discussed. Label is the smallest currency you can really expect to work with in terms of anything you can observe or reason about. And so we'll notice some interesting things. For example, server reading a message cannot be the first thing that happens in a system, because to read a message, someone has to have sent one. So either one of the clients would have had to have sent a message, perhaps even both. You can send 2 messages and then read one. That can happen. After that, once the server reads a message, well, the client still can't receive a response because the server hasn't responded yet. That happens in a second label. So again, you have some other possibilities and impossibilities, and no concurrency in this step. Then when the server sends a page, at that point, one of the clients will receive that, and that will depend on who the server sent it to. But at this stage, not both, because it only sent one. If you send one and receive 2, that wouldn't make any sense. And so forth for a very long graph. Even this graph as it is not complete. Feel free to look as a mental exercise to see what transitions and what relationships we might have missed out. But in any case, hopefully this illustrates how TLC sees the world and how we have to make things look to have the MPCal generated code actually make sense. So, about that. First, let's discount a trivial solution. It's possible you could make some kind of heavyweight distributed scheduler that uses some kind of consensus protocol to just agree on what orders are reasonable and just do that. Unfortunately, that would be really hard, really inefficient, because it has to run consensus every single time something does anything. And also, it's really not how distributed systems work. If you ran things on that, you wouldn't be able to generate a reasonable implementation for most protocols you'd even care about. So our actual goal is achieve as much concurrency as possible and try our best to exploit all the interesting features of these algorithms that mean things don't actually have to be quite done in a strict order. For example, if there's no conflict between the externally visible side effects of something, then it's fine to be more concurrent than the model might otherwise imply in a strict sense. Of course, we want to do this safely, so we need to build a system to reason about this whole situation. First, just to get out of the way, if it didn't happen to a resource, it didn't happen. If a step does not touch anything that could possibly interact with something with sharing, in an archetype, that is, its parameters. So if it doesn't write to the network, if it doesn't write to the file system, if it doesn't change any state, it might as well not have happened, or otherwise you could say it could have happened at any time. So that's a nice simple case, and that can also partially apply in more complex cases. That's the happy path. The tricky path is when we really are dealing with interactions with the same thing. For example, you're reading and writing to the network. That means you have basically a concurrency hazard, and our resources need to be able to express when it is or isn't okay to do a certain thing. Of course, since we don't know anything about how our resources actually work, in terms of the model, we just need to let the implementation decide what's safe. If you need to do something like exclusive access with locks, your implementation should be able to do that. You should also have the freedom to run arbitrary protocols inside the resource to determine what is or isn't okay. And while those protocols should ideally be simple, you can really do whatever you want. Now, to explain a little bit about why we seem to be so intent on not understanding what the resource does, a problem that you need to understand about why we can't use more static things, at least in the general case, is half the time we don't even know which resource we're talking about. So resources can be accessed based on runtime values within the same label. So essentially you could compute a value in arbitrary ways, including getting it from another resource, and then you could use that to access by key another resource and do things to that. And sure, in some cases you could probably figure that out with static analysis that's sufficiently smart, but it is not generally sufficient. Static analysis will have a point where it has to be conservative and can't answer your question. So ultimately we will need a general runtime solution, and so we focused on one. So how do we, at the end of all of this, actually execute an atomic step in Go? So we basically have modeled this as a local consensus step between resource implementations. We'll try to execute steps concurrently, if at all possible, and just speculatively do whatever we think might work, and do that as long as the resource implementation consider it safe. And that consider it safe part is the local consensus step. This is not global. This doesn't go outside of even the same archetype, even if you have multiple archetypes running on the same process on the same machine. This is literally a strictly local thing that happens to determine whether a label is successful or not. So to outline it, it's very similar to 2PC. We're strongly inspired by that very general protocol. So what you'll do is you'll speculatively try to execute all the statements in order. You'll make whatever non-deterministic choices seem reasonable. You could even just toss a coin to see which branch of a non-deterministic choice you might take. And at any time, you might discover that you can't take that path, and so you can just give up, because everything is speculative at this stage. You can do that. Then, at the end, what you do is you run a pre-commit step, which says essentially it's the same. It's like the step of the same name in 2PC. So you determine if the resources can be considered to have been successfully changed, and you seek consensus on that matter. And if that's considered okay, you commit, make all the changes visible, and your step has officially happened. Otherwise, you will abort and try again. Maybe you'll take another branch in non-determinism. Maybe you'll observe something different from some resources. There are all sorts of reasons you could end up succeeding the second time. And so that's how that works. Now let's look at this as a nice diagram, just to make sure we understand how the flow works here. So you can run through a critical section. You start outside a critical section, and the happy path, which is bolded, will go through reads and writes. When you start reading and writing, you're in your critical section. You can abort at any time. Once all of your reads and writes are done, you go to pre-commit. You see if it's reasonable that this is a valid state. If so, you commit, make everything visible, and you're done, and everything, including pre-commit, can lead to a full abort of everything. Ideally it doesn't, but it could well do so, and it can help a lot of implementations to allow this. So lastly, let's have a quick look at our super general API that we've been justifying and explaining this entire time. So at the top, we have read value and write value, which allow you to speculatively manipulate the resource's internal state. We have pre-commit, this query which asks, is this okay? Could we commit and have it reasonably succeed? We have commit, which is the only way for anything to officially happen. Once you call it, the resource will commit the changes made to it, and at that point you have finished your code section. You have abort, which unhappens whatever has been happening, and you will use that if something determines that we cannot reasonably proceed. And you have this little index accessor, which is the source of this consideration for runtime indexing of resources. So resources can have sub-resources, and those sub-resources behave exactly the same way. There's nothing special about them, theoretically speaking, but it's important to understand that that can happen. Now, let's have a look at our distributed runtime. So far we've been talking about roughly the abstract relationship between the compiled Go and the runtime libraries. Now let's talk about actually the runtime libraries. What have we implemented specifically? So the whole point here was to make things as push-button and easy as possible. So we have a full implementation of all the TLA plus value operations. If TLC can execute it, probably so can Pico. We have all the scheduling framework for the algorithms we've been discussing so far implemented. And we also have a variety of hopefully useful resources that we built up as we tested and tried out different things with Pico. And we'll now talk a little bit more specifically about some of these, which are maybe not the ones you might expect. Of course, we provide lots of low-level resources with very simple implementations, but we have some interesting ones too. So, distributed global state is a thing that you wouldn't normally expect to want, but sometimes you just want that. I mean, think of any app you've written that uses etcd to store metadata or something like that, or if you've seen an algorithm written abstractly using this kind of model, you might want to be able to run it. We don't guarantee it will be necessarily the most efficient thing if you write your entire MPCal model in terms of this, but it could in principle be executed. And that's important to provide. Also, if you want to be using distributed global state, but to have it work maybe more efficiently, a good way to do that is to use conflict-free replicated data types, CRDTs. And we provide support for a couple variants of those, and presumably you could add more if you needed to. So if you're writing something in that style, we can support it as well with our general API. And we provide a couple of built-ins. So the other thing that is important to know as a workhorse resource type is failure detectors. MPCal doesn't really have an official model of failure. It doesn't have like a fail or otherwise kind of instruction. Instead, and neither does PlusCal nor TLA Plus, it wouldn't really make sense to have something like that. So instead what we do is we provide a failure detector resource, which basically lets you ask, is this node up? What's nice about this is because resources do actually have a complete formal model in terms of when you're model checking, you can explore the kinds of outcomes that can happen when you ask a failure detector, is this up? You can also model more or less pessimistic failure detectors, for example. And when you run with an implementation, you can pass in that failure detector and actually run a real one, and then you can write statements like the one on the bottom right, where either you can read messages from the peer or send things to the peer, Or you might be catching a failure, and in that case, you can take the other branch and handle that failure in some way, and that is fully applied to your model. The model checker takes it into account, and it runs at runtime. And this is an important thing, and we've used it a lot in a lot of our prototyping sessions. And lastly, and possibly most unusually, it's important to understand that Pico can generate implementations for a lot of things, which includes our own archetype resource API. So not only can you handwrite implementations of it and hope they are correct, you can also use the correspondence between message passing and object-oriented APIs, like the one that we have, and you can implement your resource in MPCal on top of other resources. We provide all the glue code that allows you to stick this together at runtime, and you can separately model check your resources if your resource gets complicated and you're concerned about its reliability. So that can be quite useful. Now that we've introduced a lot of things that we've made, let's evaluate them and see how they do. We have three main questions for our evaluation. So, in general, what's developer effort for actually using MPCal, writing things in it? How do the systems we generate perform? If they perform terribly, that might be a bad thing. And how do our verified resources perform? This is a specific separate question because it might be that our implementations are only fast because of handwritten resources. And if you stack Pico-generated code on top of itself, maybe that performs notably worse. So we want to answer that question. To summarize what our implementation is, it's currently about 6,000 lines of Scala, about 2,000 lines of Go for the core runtime with all the scheduling functions and basic sort of scaffolding, and we have 4,500 lines of resource implementations, which are all those implementations we were just talking about a moment ago. We can compile concurrent and distributed systems. The concurrent part hasn't been well evaluated, but we use multi-threading in our distributed system models and implementations and so forth. And it's a reasonable thing to want to do, even in a distributed context. So that's why we say that. And we also support quite a lot of resource implementations, and it's an open API, so you can add them. For now, though, what have we actually built? So we've written a few specifications. Our flagship specification is basically a port of the original Raft TLA Plus specification that came with the Raft paper, and we built a key value store on top of it. All these times, by the way, are in terms of effort by 2 graduate students, and so it took about 15 days to port Raft properly, make sure it still model checks, all that kind of thing, and 10 days to build a key value store on top of it, which, if you think about how long it took to build something comparable with a piece of related work, Verdi, for example, at least 1 year of people working on it, then that seems quite promising, really. We also specified a few other things. So we've got a primary backup replicated key value store. We've got a verified CRDT resource, which is our proof of concept for a resource whose implementation is generated by Pico. And we also have our CRDT resource, which is handwritten, but follows the resource API and is a non-trivial resource implementation for eventually consistent distributed sets. And all of these took between 7 and 10 days to specify, keeping in mind for the last one that to specify a resource, to use a resource, you have to also specify it. So even though the implementation is handwritten, the specification is still there and is applied to the specifications that make use of that resource. So, having seen that it's pretty reasonable to use MPCal in terms of writing specifications, when we generate implementations, how do those perform? So we've evaluated 3 instances here. Our flagship specification, again, is we compare it against etcd, industry mainstay that you've probably heard of, also written in Go, and Vardi, the generated implementation by Verdi of the same key value store. And we run these on the YCSB benchmark, common benchmark for key value stores. We also test our verified CRDT resource against a handwritten Go implementation to see what kind of overheads there are there. And we compare our eventually consistent distributed set resource to SoundCloud Roshi, which is a popular implementation of a very similar data structure, which is handwritten and is used by SoundCloud. Our experimental method is based on Azure Cloud. We used Ubuntu 20.10 machines of the standard B4MS type as of late 2021, and we repeated all measurements 10 times. You'll see 90th and 10th percentiles on our plots, and we tried to configure systems as best we could as off-the-shelf deployments. Notice one oddity in some of our graphs. Vardi turned out to not support large keys because of an assumption it made about the UDP protocol. So it would lock up if you threw too much data at it. So to get actual results that were comparable to Vardi's results, we reran all of our other experiments with the same small size key variation that we had to use to get Vardi to run at all. These keys are, instead of the generated keys from YCSB, they're things like 1, 2, 50, just as strings. So, first we ran all of our key value stores on the YCSB workloads we support, and we measured throughput in operations per second. So you'll notice that all the systems responded quite similarly to the different workloads relative to each other. Also notice that while we did do the work to account for it, the small keys modification doesn't actually change very much about the performance we notice. So that's good to know and means we don't have to think very much about that. And, most importantly, notice that while etcd does much better than all the other things we measured, we're actually comparable to state-of-the-art in terms of performance, despite having spent much less time on our implementation and verification steps. So, going further, we also measured throughput for different cluster sizes for the Raft KV stores, and we noticed that, as you expect, with a larger cluster, things get a bit slower because you have more nodes to perform consensus with. And again, etcd does a lot better, but otherwise we seem to be roughly comparable with the state-of-the-art, and that's still nice. Also, here's where something gets a little interesting. We also plotted latency against throughput for varying load factors, and this shows us something a little interesting, actually. So, of course, etcd does really well, and Pico and Vardi do comparably, but what's interesting is that while Pico seems to actually have better latency, so lower latency, across its throughput range, it seems to have quite unstable performance. So we had to think about why that was, and we think it's to do with how Pico relies on non-deterministic execution to express certain constructs. So our current implementation is quite simplistic, and as a result, while it does get us to MVP very quickly, we have to reconsider that, and we have some ideas about it. So we'll talk about those shortly. Also, we checked properly that we actually support our failure models in practice. So we used those failure detectors, and if you plot throughput over time for a single run where you simulate leader and follower failures, you get what you expect. When the leader fails, you get a little dropout because the leader was the one processing requests. And when the follower fails, you don't see much of a change because the leader just has to stop trying to do consensus with the follower. And we recover from both of these and seem to keep running, so that's promising. Now, for our last comparisons, we have to measure something a little bit different. So previously we were measuring throughput, but in this case we have to measure time to convergence, which is a specific measurement for CRDTs. The issue is that if you just measured throughput, CRDTs can trivially just not synchronize. So if you run a lot of requests, the CRDT might just say, okay, to all of the requests, you appear to have completed everything, and only then does the CRDT do the work necessary after you're done to synchronize everything and actually achieve any kind of consistency at all. So what we did instead was we ran all the requests, and once we were done, we waited until all the CRDTs had the same state between each other. So this would actually measure how long it takes to propagate information in a CRDT versus just how long it takes for a CRDT to say yes and do work later. So on the left, we have our verified resource, which we compare to a handwritten implementation. And the results seem quite promising. There's not a great deal of difference between the implementations. And as a result, while this isn't very conclusive, it means that our generated implementations can reasonably work when used in this way. On the right, we compare with SoundCloud Roshi with our handwritten CRDT implementation, and we notice we do a lot worse and scale quite badly and unstably. So there's a couple of reasons we think this is that we think cause this. In our implementation, we use vector clocks, which don't scale as well for many nodes, to track causality and figure out the updates properly. Whereas Roshi uses timestamps, which seems to be more efficient, though a bit harder to verify. Also, it's worth noting that with our very large error bars, it could have something to do with our handling of non-determinism, which we should discuss right now. So we noticed that there's some issues with any code that has non-determinism, so any code that has like select type constructs. Exploring non-determinism can be expensive in our case, and we're also a bit concerned about, since our implementation is highly dynamic, we could also be falling victim to some pessimistic concurrency control and measures like that. So we're working on the first problem, which is to try and handle non-determinism more intelligently. Currently, when we try to explore branches, we end up essentially picking one and seeing what happens, which means that if you try to read from something and there's nothing to read, you might time out for a little moment and then go back and try something else. And if you make wrong choices repeatedly, you're going to spend a lot of time waiting for something that's not going to happen, even while another buffer might already be full. So our ongoing work is essentially to try and concurrently explore the branches without this little waiting game, which is much closer to the real select type constructs you would use in an implementation, and will hopefully put a huge dent in this issue and make our performance much stabler and, in some cases, much better, ideally. We're also considering, but not practically exploring right now, the opportunity to leverage static analysis and model checking, since we have a model in MPCal, and we could try to use that to selectively avoid the costs of certain implementation choices that are only made to be pessimistic. So we're considering that, even though we haven't considered it very much for the moment. Also, the other big point with Pico is verified compilation. So we trust a lot of things in Pico's implementation. We trust that Pico itself works properly. We trust we got the runtime right. We trust the TLC model checker is correct in what it tells us. We trust all the runtimes of all the systems that we use, etc. Verified resources are a decent step that we already have, in that maybe you don't have to trust your resource implementation so much if you've model checked it. That would be nice. But ultimately, we have this problem of a lot of interacting components, and any one of them could be a bit wrong. So we are working on a trace-based verification system to run actually at runtime. So imagine you've already model checked your system, you think it's probably good, but you want to be sure that the system you're deploying is the one you model checked. So what you do is you automatically generate some very precise instrumentation for the generated system using the MPCal model as a basis. And then you compare the traces that your system generates with what the MPCal model actually says. So what this means is if you configured your implementation wrong and it does something the model doesn't allow, you'll find out. If your model assumes things that aren't really true about time or networks, or similar to the situation with Vardy, where it assumes that you can send infinite-sized packets on a UDP connection, which is not true, you will find out. And if your handwritten implementation of some resource is wrong, you will also find out. So this seems quite promising, and we are currently actively working on it. To summarize everything we've been talking about so far, we've presented MPCal, which is a modeling language that cleanly separates the system you're trying to build from models of its environment. This design decision allows us to make Pico, which generates correct distributed systems, we hope, from these models that have been model checked. Our results are comparable to state-of-the-art as far as we've evaluated them, and that state-of-the-art takes a lot of effort to verify, so our lighter weight setup seems to be quite promising in terms of being able to spin up quickly. And we are actively working on improving Pico's output and ability to generate production quality systems code, or be part of it. Notice on the bottom right that we are an open source project at that URL, and this is normally where I'd open for questions if this was live, but this is pre-recorded, so feel free to send in your questions via whatever medium you like, GitHub, email, and so forth, and we hope this has helped you. Thank you.